So hello everyone, and thank you for being here. Today we have at our talk Jannes Münchmeyer. We will talk about the importance of developing open source tools in science from the point of view of a developer. He will also introduce shortly two projects he has been working on, SeisBench and PyOcto. Just a couple of things about Jannes. Jannes is currently working at ISTerre, but he did the ES PhD at GFZ / Humboldt University of Berlin on real-time assessment of earthquake with machine learning. Even if the topic is earth science, his PhD was in computer science. So Jannes, after his PhD, came to ISTerre, in which he has been working from 2022. He started a postdoc, and then after a few months, he won a Marie Curie postdoc. He's working here with Ansoke on searching low-frequency earthquake to understand slow deformation in subduction zone. So this is it. I hope I didn't made any mistake. Otherwise, Jannes, you can correct me. And I'll give you the word.
Yeah, thanks for the invitation, the kind introduction. No, I can confirm you did not make any mistakes, Mirko. That's all correct. I'm right now here at ISTerre working with Anne. But so when Mirko asked me to do this talk, he said it's a pretty liberal format. And I decided that Friday afternoon at 4, I don't really want to give a hard science talk. But there's another topic that's dear to my heart. And I decided I want to give a science policy talk. So this is a science policy talk, and maybe also a bit of a disclaimer that it's one of these talks where the speaker does not have many references, but a lot of opinions. So this is mostly a collection of thoughts and not like a very well-formed presentation that you'll see now. I'll start off and talk a bit about SeisBench and PyOcto and a bit about what science I do as an intro to motivate what I want to talk about. But then it's more about what I think I've learned about open source and what I think is important about open source for seismology or for science, but especially science as in seismology, which is the field that I know about most. So let's start off. Right now, one of my main projects is building an earthquake catalog for northern Chile. So we have lots of temporary deployments, and this is the current intermediate result that we have. So these are these high-resolution earthquake catalogs. Now, how do we generate such a high-resolution earthquake catalog? Basically, it's a multi-step process. The first thing we have is continuous waveforms. So that's what we collect at the stations. And then you need to pick phases. You need to pick the P and S arrivals of these stations. And since a few years, the state of the art for this is definitely to use deep learning. So in my case, I use the SeisBench library for doing that. And then I get this. I get a list of phase arrivals. Once you got a collection of phase arrivals, that still doesn't give you the events, because you need to know which phase arrivals belong together to then locate the events, and there will be false pickers as well. This step is called phase association. So you basically go from what you have here on the left. This is just in a 1D example. So we have time on the x-axis and just like one dimension on the y-axis. It's like earthquakes on a string. And we have all the picks, the P and S picks marked in orange or yellowish and green. If you look closely on the left, you could probably spot the two events, but on the right, they're also marked with the red stars and then the move outs, and the rest are false picks. So the problem is a little more complicated, but it gets to 3D. And I use a tool for this that's called PyOcto. And then if you put this together, we basically go from continuous waveforms to phase picks and then through association to an earthquake catalog. In this catalog, you can also already see the subduction that's happening in Chile, but you'll also see stripes that are very much not there in the real earthquake distribution. That's because PyOcto has this artifact. Turns out most phase associators have such artifacts because phase associators are built to figure out which groups of picks belong together. They're not really built to give you great locations, because for that we have tools like non-deadlock. So traditionally an earthquake workflow will then add a relocation. Well, maybe we could just call it an absolute location step. It's happening afterwards. And this is like the very basic workflow to build earthquake catalogs. Now there could be much more. You could try relative relocation, you could estimate magnitudes, moments, and so on. And that's a basic workflow. Now, normally when I give this introduction, I'd now say, okay, and if we look at low frequency earthquakes, why does this not work? But as I said, today I don't want to talk about science, but I want to talk about open source. So if we look at this, then all the way on every step, we have open source tools. We have SeisBench, that's under GPL v3 license. We have PyOcto under an MIT license. We have NonLinLog under a GPL license. And that's just the tools, because if we look from a different perspective, there's open source all the way down. SeisBench builds on OpsPy. OpsPy builds on NumPy. NumPy builds on Python. All of this is open source. My laptop's running on Linux. Every server basically nowadays is running on Linux. Our server has a Slurm cluster running on it. Slurm is open source. So indispensable for doing the basic task like building an earthquake catalog is this huge collection of open source software that is either extremely domain specific, such as the top layer here, slightly less domain specific as OpsPy or NumPy, much more general even, or very, very general, such as Linux. And because all of these tools, and there are many, many more I could put on the slides, that's essential, that's what I want to talk about today. So my rough roadmap is this. I'm going to tell you a bit more about my personal experience with open source as a developer, and then I'll say why we need open source, in my opinion, and how to do open source. And in this process, it will also be about where I see the challenges in actually building open source software. So let's start off with my own experience with open source. I have two main contributions to open source. So I've developed together with another PhD, and I'm maintaining SeisBench, and I've written this PyOcto library. I've also contributed some code snippets to other libraries such as OpsPy, but by far not to the degree as I'm involved here. So let's focus on these two things. And I'll introduce these projects a bit to give you an idea of what it's about. So SeisBench is an open source Python framework for machine learning and seismology. As far as I know, there was a workshop about SeisBench at one of the SPIN meetings, the one in Scotland. So many of you might have seen this already. Basically, SeisBench consists of three main parts. It consists of data, so these are benchmark data sets. It consists of models for doing data processing, such as, for example, or mostly face picking using deep learning, and then generate, which is a part that brings the data and the models together to actually train the models. What's important is you can use any of these parts separately. You can just use the data, or you can use the models without training them yourself, because SeisBench has them trained. At the moment, we have 16 data sets in there. So they're the 12 that are plotted. There are 4 that we don't actually have location information, and so I can't plot them. But there's quite a diversity. We have a bunch of different regions like Switzerland, Italy, the Pacific Northwest, Texas. But we also have global data sets that compile information from many local distances, but all over the world, or teleseismic events. We have depth phases, and we also have OBS data sets, so ocean bottom seismometers. And all of these data sets are now in the same format and have the same API to access them. So you can just exchange them in your workflows because they're all in the same format and the same way you access it. The second important part is that we have these benchmark models. Many of you that are in seismology have probably heard of EQ Transformer and PhaseNet, the two most prominent picking models. So all blue ones here are picking models that figure out when phase arrivals happen. The green ones are denoising models that try to reduce noise in a continuous seismic trace. And the yellowish ones, these are depth phase models. So what they try to do is figure out, so they also pick to some degree, so they pick depth phases, which is a way to figure out a teleseismic distance, how far an earthquake is away. And at the same time, they also all have training pipelines, so we can connect them to the data. So you can train them, but you can also just apply them, and they all have the same interface. This is a very short overview of what SeisBench does. Now to the question, how did we actually build SeisBench, or how did it came to be? Essentially, it came to be because we had a project that was financed by Helmholtz AI that encompassed 2 PhD students for 1 year each. and it's done in late 2020. Helmholtz AI is the AI initiative of the Helmholtz Association, which is one of the biggest research organizations that exist in Germany, for the ones who are not in the German research system right now. And the original objective of this project was collect benchmark data sets for seismic phase picking, compare existing models, and extend the methods to teleseismic and OBS data. You see that SeisBench goes a little further than that, but we figured out rather early in the project that if we already collect benchmark data sets and bring them to the same format, and we can collect models and want to make them all accessible through the same interface, it makes sense for us to build a library that really encompasses all of this. And then we released SeisBench 01 in late 2021. Now we had SeisBench 06. So what has changed since then? There's a bunch of additions. So we have 5 new data sets, of which 2 are internal. And when I mean internal, I mean by people that were associated to the original Helmholtz AI project, people like me or the other developers. But we also have 3 external data sets. We got one from the NEIC in the US, we got one for the Pacific Northwest, and very lately the one for Texas, where just people that were not associated with us have provided data sets in the right format and then integrated them. There are 2 new models, but both of them were written internally. There are 2 sets of model weights we got externally. There's quite a lot more on examples and documentation, of which most was written by us. And then there are many improvements to stability, performance, usability, like small feature additions, which are a wide mixture of internal and external. So it has evolved quite a bit since the original versions in the last 2.5 years. Now, how is it actually developed and maintained? I've mentioned that we had 2 original developers. Now, both of us finished our PhDs. The other PhD went to industry, so we are down to 1 maintainer right now, which is me. We have 13 contributors according to GitHub, of which 9 are external. So there are quite a few people. For the external side, usually they have like 1, maybe 2 pull requests, which is very valuable, but it's not a regular contribution. But we have around 200 external issue reports, feature suggestions, pull requests, just checking GitHub. That does not account for people who just write me emails. So there's definitely quite some community engagement here. Now, one question that's interesting is how many people are actually using it. We don't know as the first degree answer, because in the end, it's a library. People can just download the code, install it, run it. And there's no need, like no way we can absolutely know. But what we can track is we can track how many people actually check our documentation, which is sort of a proxy of users. Clearly, some users will not check the documentation online. Some users will check the documentation, or some people will check the documentation but not use it. But it's a good proxy. And roughly, we have 500 people a month at the moment, with a growth year over year of around 100%. So it's at the moment roughly double of what it was 1 year ago. So it's still clearly growing the user base. And if you check countries, it's quite distributed over the world. Clearly, there are zones that are most active, which is North America, Asia, especially China, Japan, Taiwan, and Europe. But also you see access from other world regions, with a bit of an exception for a large chunk of Africa. But that's kind of the orientation. This is a library which seems to have around 500 monthly users distributed over the world. Now, that's SeisBench. And I want to contrast this a bit to PyOcto. So all I want to say about what PyOcto does is that it's a high throughput seismic phase associator. It's easy to use and achieve state-of-the-art performance, even on dense seismic sequences. So it is a program that goes from phases to events. How this works internally is a story for a different talk. But what I want to highlight is that it's very much a single purpose tool. It's not like SeisBench, a lot of different options, but it's one thing that does one job. A bit more for the background. So I wrote PyOcto by myself. So it's a single developer maintainer project. There was no specific funding, even though clearly I was funded on my Marie Curie and funding I had before. And I sort of needed it for my work. So it made sense to write it, but it's not as big as SeisBench in the build up. There is no continuous development plan, so there will be bug fixes if bugs turn up, and maybe there will be extensions at some point, but it's not really a project that's meant to be alive, and it's only half a year old, so it's pretty recent. And if you check it, the user base, well, it's only 80 active users last month, so much smaller. And the distribution is somewhat similar to what we see for SeisBench, even though clearly not as diverse. So I'm mentioning this because it's kind of the opposite to SeisBench in that it's much, much smaller and like not continuously developed in a single development. So that's my background. That's what I do in open source, and that's my perspective on open source of like writing and maintaining such software. So the question you might ask is, why should we use open source in seismology? And I want to mention 5 points today. The first is open source accelerates science. And there are multiple ways to show this. I think this graph is actually a good point. Assuming we have 500 users, they're all enabled to use certain tools with much less work to put in. So for example, if they can use SeisBench, they can use deep learning phase pickers. They could also do this when they use EQ Transformer or PhaseNet, which are also open source codes. But basically, one of these 3 libraries is what you need to use if you want to do deep learning phase picking. If you don't use one of these libraries, or if they all wouldn't exist, you'd have to write it yourself. I would presume that 95% of people that are now using deep learning phase pickers would resort back to an STA LTA. So people would either spend a lot of time on this to build it themselves, or they'd have to go with worse options. So open sourcing models, open sourcing code enables people to use better things, to use better tools. And if we have better tools, we'll find, for example, more earthquakes. We'll be, with less time investment, get to the same results. And that's essential for faster science, that we can produce detailed results with the time available to us. As you can also see this, if you just check, for example, for OpSpy, which I guess we all know in seismology, we have 1,300 citations and probably 3 times as many papers that use OpSpy and do not cite it. So it's very vital for us. And if we didn't have OpSpy to use all the functionality and we'd had to code this all ourselves, we would probably take a lot longer and the science would be slower. And even more substantial for tools like SciPy that's lying under all of this, which has 25,000 citations and a similarly high number of not cited usages. The second point I have is that open source improves accessibility. Now, we all write, or many of us write code. And if we don't publish code, it still happens that we talk to a colleague and we're like, I can give you my code, or they're like, can you give me that code? And we'll share code. So if we do not do open source code, we'll probably still share code. The problem is we'll share code only with the people we know. We'll share code with the people we meet at conferences. We'll share code with people that we are at the labs with. And if you look at this maps, there are enough countries where it's pretty clear that not many people in these countries have the opportunity to fly to HU or EGU. So for many of these people, open sourcing our code is a great way to actually make it accessible, because these personal links that otherwise would be used for code sharing are not actually just like available for all the potential users. Third part, open source improves trustworthiness of results. So when we wrote SeisBench, as I said, the plan was doing this benchmark, which we did. We published this in early 2022 in JGR. Paper was well received and cited. And if you go to this article now, you'll find this remark at the bottom, which says that in March 2023, we published a correction. Now, why did we publish a correction? We published a correction because it turns out that our implementation of PhaseNet was completely wrong. And when I say completely wrong, I mean it was untruthful to the original implementation in quite significant detail. And the only reason why we knew this was that 1 year after we had published this, Yuan Zhong opened an issue on GitHub asking, is the PhaseNet architecture the same as the one in the original paper? And he detailed a bit what he thinks the differences are, and he was absolutely right about this. We had gotten it wrong. So we fixed it, we rerun the benchmark for PhaseNet, we updated the results, and it actually made a bit of a difference. It's not massive, but it switches from PhaseNet, EQ Transform, and GPD are the best models to PhaseNet is the best model, closely followed by EQ Transform and GPD. And it's not only that we now fix this bug and that our benchmarks right now, but it's also that if people use an open source code that many people use, it's just much more likely that these bugs are going to be found. Like everyone's going to code bugs, but if you only use your code alone, it's less likely to find these bugs. So battle-tested code is usually more safe. Along the same line, open source improves reproducibility. Many of you have probably heard about this debate about the paper by Quentin Blettery, the precursory phase of large earthquake. It's a science paper from last year where he says he finds a precursory phase of large earthquakes in a certain analysis of the geodetic data. Now, a while after he had published this, there was this blog post on the blog of Kyle Bradley and Judith Hobbes, where they do not believe the claim, and they did an additional analysis, which in their view proves that the claim is wrong. I don't want to take a stand on this issue, but what's interesting is what they write in their blog post somewhere, which is the statement I put on the bottom right. Before we proceed with our work, we want to thank the paper's author for the very nice code and data that were provided in the supplementary information. The high quality and clear organization of the supplemental data has allowed us to do a detailed re-examination of their study by following their analytical workflow exactly. We were able to replicate the figures in their paper within about an hour of starting work, with most of that time dedicated to the usual boring Python environment configuration. From there, we could write our own snippets of code to modify the input data and make some charts and maps. And we then simply ran their workflow again to produce new figures directly comparable to the publication. This is an exciting way of doing critical science, and we're indebted to the authors for their efforts in this direction. So I think that sums it up quite well. They had a doubt about Quentin's study, and they wanted to check this study, and the way they could do it, or the only reason they could do it, was because the data was open and because you openly shared the code. So even though for him, you could say it has a bad consequence that his study is publicly doubted, for the scientific progress, it's extremely valuable that we can do these comparisons. And my last point, I think open source bundles resources. I sum this up with this extremely simple formula. The number of users is much, much bigger than the number of contributors or developers. That's the case, that's fine, and that's also how it needs to be. But what that means, on the other hand, is that if one contributor publishes an open source code for something and 50 people use it, we'll have a massive time saving over the community. So in terms of resources, we save. If everyone does this, we all save on time. And because the alternative is that users either don't do these things or users write it themselves, and we'll have the same code sitting on many private laptops. Okay, now I've given a lot of opinion why we should do open source, which leads me to the last big point, how to do open source. And I'm going to go a bit through what I think is the key point, and that might sound intimidating, these key points, but then I'll also show that you can do it more easily as well. So how to publish an open source code? The first step is write the code. I would say best practice helps a lot. So things like structured code, use classes to properly structure your code, do unit tests, use a code style, and so on and so forth. But when I say best practice helps, it's not absolutely necessary. It depends very much on the case, how much best practice you should use. So I wouldn't be intimidated by this step. Second point is document it. It's important to document. You need a comprehensive reference because you don't want people to have to look at the code to figure out, reverse engineer the code to use it. So what the code does needs to be properly documented. The code that just has the code, but is not usable by someone who hasn't written it, is not a useful code. And the most useful part is click and go examples. So when we wrote SeisBench, I somehow had the assumption that people would read the documentation when they want to use it. And pretty quickly, we realized that's not the case. I mean, yes, people use the documentation, it's important, but the way to get into a new code is to look at the examples and then modify the examples to your actual needs. So for documentation, it's very important that people have a simple example that they can just run out of the box. Okay, we have code, we have documented it, and we need to make it available. First step about making it available is put it on GitHub or a similar resource, so something transparent and that has a version management and an issue tracker best case. I see there's something, is there something on the chat? I can. Nico, is there something on the chat to see the number in the corner?
No, that's okay. It's just a comment.
Okay, good.
Yes, but yeah, we can talk about it later.
Okay,
I would
we
say
do
you
this
can
at the
continue
end.
with your
Great. I can just see the tiny one in the corner. So make it available. So we should have it somewhere in the version management. It should definitely have a DOI, so persistent identifier, so that it's citable and on the long term available. And you should, best case, put in a software repository, something like PyPy, so you can just do pip install. But there are others for other programming languages. The reason why is it's convenient, and convenience is extremely important for software. And then you advertise it. You write a software application, you go to conferences, you do tutorials, you put it on your Twitter, on your Blue Sky, on whatever social media you use, so you advertise it. These are the points basically up to publication. And then there's one point which is a long-term commitment, which is maintain it. An open source code that's not maintained is a lot less useful than a maintained code, because users will have questions. So you need to answer user questions, and the code is usually going to have bugs. And it helps a lot with user credibility if you provide bug fixes. And maintenance can be a lot of work, especially for projects that grow bigger and are active for a long time. And this is also where the best practice comes in again. If you write code with coding best practice, it's much easier to write bug fixes, also receive bug fixes from other people. It's easier to add features if you have unit testing and continuous integration. So it helps with maintenance if you do that step right. Now, I've talked about how to do it. Now, the question is a bit, why should I do it? And I think that's where it gets really tricky in science. So I wanted to speak about funding and incentives in science. Science funding is mostly focused on research results. Yes, there are grants for method development. Yes, there are even grants for software development, but the majority of them are not. So if you look at what you want for an ESC grant, they want new science. And they explicitly state somewhere that it's about new results. So that's not really the focus there. So it's already doing open source is slightly out of focus of science funding. The second point is getting funding and recognition for code development is doable. You can write software papers, there are enough funding schemes for that. But getting money for code maintenance is much, much harder, because it's not, funding is project-based, and maintenance is a long-term job. You basically would want funding for a couple of hours every week for yourself. And then you also want recognition, assuming you're someone who still is applying for new jobs in science. And that's very difficult. Besides that, you clearly get recognition for your software, like you got cited for your original application, you get cited a lot more if your software remains usable. So there's a certain aspect of this, but it's harder. And then for open source codes, well, they're time intensive for the developers. So the developer invests a lot, and they save for the users, which means the place where the benefit actually manifests is only partially at the developer, but it's a lot of community work as well that's involved in this. And there's one thing that kind of relates to this, which I would call the legacy open code dilemma. Many standard codes we have are old. Now, going back to the example of earthquake catalogs, one standard code we use is HypoDD for relative relocation. That's been published in 2000, and the last update I could find online is from 2010. Wellest, which is for 1D velocity model estimation, is written in 1976, and the last update is about as old as myself, version 3.1. So these are very old codes. What are the consequences of these old codes? Well, first, they take up substantial time in using them. They are Fortran codes. Okay, people still use Fortran. Fortran is like a totally fine language, but then they have, for example, fixed length input. And the documentation is kind of convoluted to understand, especially for someone who's never written Fortran code, which I guess are many of us. So it takes a while to get your data into the right format for these tools and pass the output and understand some of the quirks. And the second is, well, in 1976, no one built a code that is able to deal with 500,000 earthquakes. However, that's where we've arrived now in the size of our earthquake catalogs. So we need a lot of hacks to actually make these tools usable to the demands of modern workflows. And that many people do this again and again. So we actually have many people investing work here, and I'm sure that the time that people have spent getting HypoDD and Wellest to work would easily sum up to enough time that one person could have rewritten it. So why is no one writing a new code for these problems? I think first reason is these are good codes. These are reliable codes that have been around and people stick with what they know works. So they're definitely good codes. So what we need nowadays is actually someone to rewrite the same code, not do any massive development, just write the code with a better interface, with some extensions that allow them to use them on larger scale. Now, there are examples like GrowClust, which is very similar in scope to HyperDD, which does a new method and can address larger clusters, but they're not as popular overall. And I think the problem is that just writing a new code that is the same thing that people have already done 50 years ago does not really bring you any credit. And there's no system for us where everyone pitches in a few hours to do that because you need someone to do it long. And there's no system where everyone pitches in a few $1,000s of grant money because that's not how grant funding works. And now I think it's interesting to see how this works actually outside science. And that's what I want to talk about, how open source is financed outside science. If we look at the big open source projects, for example, Linux. Linux is managed by the Linux Foundation, so the Linux kernel. And the Linux Foundation is sponsored by Intel, Microsoft, IBM, Google, Samsung, Oracle, Huawei, all the big players. Same for the Apache Foundation, which runs the Apache web server, the Ant build tool, the Kafka streaming service, like a long list of projects that they manage. They have AWS, Verizon, Comcast, Tisonet Cloud, Microsoft, Facebook, Cloudera, Google. So you have all these big companies that support these open source software. The reason is they rely on the software and they rather want the software developed altogether than doing it in-house because the result is better. Now, the foundations only manage the projects, they don't actually code it. The contributions come from developers somewhere, but in practice, these developers somewhere, people that are employed at exactly these companies, so they're Google employees, for example, that get paid to write the Linux kernel. So even though each company, these are competing companies, they've realized that it's most efficient for them to all work together and write together on the Linux kernel and the Apache software and many other projects. So what's happening outside science is exactly what I feel we are not as good at yet, building large-scale projects together. Now, let me conclude. Open source is integral for science because it accelerates the progress, it makes the work accessible, it increases trustworthiness in what we do, and reproducibility gets better. And it's also more efficient use of resources. I mean human resources here, but actually also compute resources, because if you have shared development of code, they're usually going to be more efficient than with single people, right? However, open source development is a community effort, and while our community is doing a lot, so I'm not here to say that we are not doing a lot as a community, I feel that open source development in many parts fits poorly into the incentive structures of science. So that's a bit of a negative conclusion. So let's get to how can I support open source? And I've listed these from more effort to less effort. So the most effort is open source your own codes. That takes work. It's doable. And for small projects, I'd always recommend it, definitely, and even for large ones, but it's effort. The second thing you can do is you can contribute to an existing project. You spot a bug in OpsPy, you fix the bug in OpsPy, you write a pull request. Everyone's going to be happy. The third is, if you don't have the time or the resources, or you don't feel confident in fixing a bug or some issue, but you spot it, write an issue report to an existing project. It's extremely helpful for a project to learn if something does not work, because if it works for the developers, they're never going to find out something does not work unless there's an issue report. And the least effort, cite all open source codes you use. So recognition is the key currency for scientists, especially for scientists who do not have permanent positions. And it's also the key currency to get funding for projects. So to get funding for open source codes, it's essential to show that they are used. So just by citing an open source code in your paper or mentioning it in your acknowledgements, in your data and materials section, that is what actually keeps open source codes running and alive.